Welcome, I'm Samuel Cahawijaya from HKUST. I'm gonna explain to you about our work in learning fast adaptation on cross-accented speech recognition. As you may know, English is the most spoken language around the globe, and it comes with many varieties, such as American English, British English, Australian English, or even Indian and African English. And there are many other English accent varieties out there. These varieties is actually a huge challenge for an ASR system ever since. Another problem is that the available accented ASR dataset is highly imbalanced. For example, in CommonVoice, the largest open accented ASR dataset to our knowledge, the top 5 accent in that dataset already cover more than 90% of the whole data, as shown on the distribution over here, which is way too imbalanced. To cope with these challenges, we propose fast adaptation transfer learning approach that can learn from high resource accents and adapt to low resource accents. In this work, we experiment with two different approaches, which are joint training and MAML. So, what is joint training and MAML? First, let's go to joint training. Joint training is a common technique to learn all tasks simultaneously and share information between each task. Joint training optimizes the accumulated loss over task samples. It could be either balanced or from a given prior distribution. Joint training is very straightforward. It's very similar to the basic methods to train a neural network models, where we sample a batch of training data and then we calculate the loss of the training data and then perform the updates from the corresponding loss. What's different is that in joint training, we sample the training batch from all tasks following a certain distribution. Now let's move on to MAML. So in MAML, similar to joint training, the model is trained on multiple tasks, but there are a quite different goal from joint training and MAML. In joint training, the goal is to learn the average representation over all the tasks, while in MAML, the goal is to find a representation that are easily adaptable to any new task. In this work, we adopt first-order MAML estimation. So this is the flow of MAML training. It's a little bit more complicated than joint training. And in MAML, we start with sampling meta-training and meta-validation data. For each task in meta-training, we will calculate the meta-training loss with the given parameters. For each task, we will update the parameters. So for each task, there would be a theta prime, which corresponds to the parameters resulting from the inner loop updates of the model. After that, we will use the theta prime to calculate the meta-validation loss, and we will update the model parameters based on the loss. Okay, now let's move on to experiment details. For dataset, as mentioned before, we will use CommonVoice dataset. There are different versions of CommonVoice dataset, and in this work, we use CommonVoice version 2. In CommonVoice version 2, as you can see on the table on the right, there are around 288K of audio samples with a total of around 328 hours of utterances. In our work, we use the same model for all of our experiments. We use an encoder-decoder transformer architecture with 2 layers of transformer encoder and 4 layers of transformer decoder. For the dimensionality of the model, we follow the original transformer paper, which used model dimension of 512 and feed-forward dimension of 2048. We use spectrogram as our audio input, and we also add another feature extraction layer with VGG, and resulting in a total parameters of 10.2 millions. We divide our experiment into two different regionality settings. The first one is mixed region, where we train, validate, and test on multiple region accent. For simplicity, we can imagine that region corresponds to the continent, as shown on the below figure. And the second one is cross-region settings, where we test on Asian and African accents, while train and validate on other region accents, such as North America, South America, European, and Oceanian. For its regionality settings, we perform a K-shot experiment on the test accents. So first, we split the test accents into 75% of data for fine-tuning and 25% for evaluation. We experiment with different K-shot settings from 0 shots, 5% shots, 10% shots, 20%, 25%, and lastly, all shots. The steps of running the K-shot experiment is as follows. First, we train the model with the training accents for 200k iterations, and then we fine-tune on the K-shot fine-tuning set for 10 epo, and then we evaluate on the evaluation set. We further experiment the effectiveness of MAML and joint training with pre-trained ASR model. So we first pre-train our ASR model on LibreSpeed dataset with a total of 960 hours of audio data, and then continue the training with CommonVoice training data. So with pre-training, we modify our experiment steps into the following. So first, we run the pre-training on LibreSpeed datasets for 1 million iterations. And then we continue with CommonVoice training accents for another 100k iterations. And then we follow the same K-shot settings as explained in the previous slides. For evaluation, we utilize beam search with length normalization. In this case, we use beam size of 5 and we limit the maximum sequence length of the generation to 300. We calculate word error rate as our evaluation metric. We compare the word error rate of the generated text from the model and compare it with the label text from the dataset. Now let's go to the experiment result. For mixed region result, if we focus on all shot settings, we can see that MAML achieves better performance than joint training in the all shot settings. And even further, if we check the zero shot and low resource settings, we can see that MAML actually outperforms joint training in all of these experiment settings. In cross-region result, we see the same behavior of MAML training compared to joint training, where MAML achieves a better result on all settings compared to joint training. Interestingly, in cross-region result, if we focus on 25% shots, if we only focus on the low resource accents, in here means excluding India, we can see that in 25% shot, MAML can achieve better than the all shots in joint training. We further show the effectiveness of adaptability of MAML. In mixed region settings, for MAML compared to joint training with and without LibreSpeed pre-training, and also in cross-region with pre-training, we can see that MAML achieve better performance by around 2% word error rate. While on cross-region settings without pre-training, we can see a larger gap of performance for about 4 to 5% word error rate. In this case, we can conclude that MAML can actually adapt to a new accents more efficiently compared to joint training, especially on cross-region settings. To conclude, based on all of our experiments and analysis, we have shown that MAML can be applied to build a more accent-agnostic ASR model. MAML approach can rapidly adapt to unseen accents in both mixed region settings and cross-region settings. And notably, in cross-region settings, the adaptability is much more efficient compared to joint training. And lastly, in Accented as our task, MAML approach not only can convert faster, but also yields better results compared to joint training. And we show that from all of our experiment settings. You can check our code repository on the following URL. And if you have any question, you can ask directly on the Q&A session or post it on the GitHub issues. Thank you.